Section 27.2, Young's double slit experiment. So a scientist by the last name of Young created an experiment where there's a light source of a single wavelength that's shown on a single slit to generate nice coherent light that passes through a double slit, two openings here. And so these two openings act like two separate coherent sources of light. We just saw why coherent matters. That means that if they are both coherent, they can act as independent sources. And the amazing part is, with this double slit experiment, so if you look at a screen on the other side, you'll see light waves constructively and destructively interfere on a screen beyond, where there are bright fringes, where the light is brighter, and dark fringes, where it's indeed darker. There's less light there. This is wild. Like, it's easy to just be like, okay, cool, science. But science! Like, the light is interfering with itself and producing this wild pattern. I would expect if I shone a flashlight on two slits, that I would just see two slits on a screen. But instead you see this full pattern that follows the ideas that we saw in the previous section of the principle of linear superposition. So the waves interfere constructively or destructively, and it depends on the difference in path lengths, right? So at the very center, in between these two slits, we have S1 and S2, the two sources. At the very midpoint is always going to be a bright fringe. Why? Well, it's equal path length from source 1 to the middle or source 2 to the middle. And so that's going to be our constructive interference. Similarly, we could look that if we go above the middle, if we offset, we could go high enough that L2 is exactly one wavelength longer than L1. That's going to be the condition for another bright fringe, where they constructively interfere. And in between this middle bright fringe and the one off to the side here, there's a point where L2 is exactly half a wavelength longer than L1, and that will produce a dark fringe, a place where there's somehow no light, even though there's a bright spot on either side of it. And so the resulting pattern, if you look at the screen, ends up looking something like this, where at the very center, there's a central or zeroth fringe, that's m equals 0. And then on either side of it, there's this nice symmetry. There's a dark fringe for the m equals 0 of destructive interference. And then there's our first bright fringe, our second bright fringe, and our third bright fringe on either side with dark fringes in between. And you can see it's brightest in the very center here, but still fairly bright on 1, 2, and 3 for these other bright fringes, where fringes is used to describe the whole flash of light here. So you can use fringe as like spot or yeah, constructive interference. That's all equivalent there. So let's take a closer look at the math here. I know math, but that's okay. If we want to find the condition for the bright fringes or the dark fringes of this double slit, you could show that the path length difference, delta L, how much further L2 has to go if it's somewhere above than L1, is actually given by theta, the angle to that spot of interest. And theta is related to this delta L in that we could use delta L is equal to d times sine of theta. That's noting that we have a right triangle here. So sine of theta is equal to opposite delta L over d, and we can then solve for delta L. So this gives us our path length difference in terms of d sine theta. Well, for the bright fringes, we want it to be integer wavelengths. We want it to be m times lambda. So we set delta L equal to m lambda, and then solve for sine of theta by dividing the d across, and that gives us this equation, right, where we have, if we did all the work there, it would have been d sine theta is equal to m times lambda. And all we did was we divided the d across. to get this condition. And similarly, we could do the same thing for our dark fringes. The difference just being that we want our condition, instead of being integer wavelengths, instead of being m lambda, we want it to be m plus 1/2 lambda. And so that can tell us the angle to locate where a bright fringe occurs, right? Where, say, the second bright fringe occurs, which, notice this is the m value. This is a really nice display here of that. Another thing that can be really useful in these problems is not only the angle to that point, but actually the distance from the central bright fringe on the screen to where that second fringe is. This is known as the y distance, to measure from the very midpoint center up to a fringe of interest. And if you know the angle theta, which you can solve for it here, noting that we could take the inverse sine of both sides, so we'd get theta is equal to arc sine or inverse sine of all of that there, so m lambda over d. So we can solve for theta. Once we know theta, we notice that it's related to this vertical y distance by the distance L from the slits to the screen. We have a right triangle here, so we notice we could use tangent. Tangent of theta will be equal to y divided by L, opposite over adjacent, or we can solve for y and say that y is equal to L times tangent of theta. So that's a really useful equation that the book doesn't emphasize particularly well. They just assume it's obvious, I think, from the geometry, but really helps to have it highlighted. At least helps me. Maybe helps you too. Right, so let's look at an example of this. Young's double slit experiment. Red light, 664 nanometers, is used in Young's experiment with slits separated by 0.000120 meters. The screen is located at a distance 2.75 meters from the slits. Find the distance on the screen between the central bright fringe and the third order bright fringe. So notice, if we think about what we're solving for here, it's that variable that I just talked about. It's asking for the distance between the central bright fringe and the third order bright fringe. It's asking us to solve for y. Now the central bright fringe, we already know, has an m equal to 0. So that one's easy. The third order, we want to be careful on, right? So that's something to think about, but that's an important clue on this problem. That we want to pay attention to the third order bright fringe. What's the other information here? Well, there's this distance, 2.75 meters from the slits. So I would say that that is our L value. Sorry, point doesn't work very well. And then there's this slit separated by 0.00120 meters. What quantity is that? Well, remember the slit separation is d. I don't know how well I highlighted that before, but little d is equal to that 0.00120 meters. And the red light is, it tells us the wavelength of it, 664 nanometers. So this is a great observation of noting all the information given to us. And so we take a look, right, and we can solve first for theta using our condition for bright fringes. And it's inverse sine of m lambda over d. And notice lambda is our wavelength, where 664, the nano, becomes 10 to the minus 9 meters. D is written in terms of 10 to the minus 4, but you can also write it as 0.00012. And then m, because it's a third order, is equal to 3. So m values are very confusing, so this is important to focus on and make sure that you understand that. Once you solve for this angle, then we can plug it into our y equation. Y is equal to L tangent of theta, We already observed L is equal to 2.75 meters. Tangent of 0.951 degrees will give us an L distance of 0.0456 meters. So it's actually a pretty tiny distance compared to nearly 3 meters away from the screen. That distance from the central to the third bright fringe is less than 5 centimeters. So that's less than 2 inches away. Very small, but it's an effect that can be observed, which is part of why it is so powerful. Now let's finish with a conceptual example, white light and Young's experiment. So the figure here shows an actual photograph of the experiment someone did. It illustrates the kind of interference fringes that can result when white light is used in Young's experiment, the double slit experiment. Why does Young's experiment separate white light into its constituent colors? In any group of colored fringes, such as the two singled out, why is the red farther out from the central fringe than green is? Why is the central fringe white? These are some really important questions here, so I encourage you to pause and think about it for a moment. Okay, I'm going to hope that you did that. The thing that we want to think about is for these colored fringes out here, they're all at some angle theta from the center. And we could find that angle given the condition for where bright fringes are located, right? We know that they're located at angles of theta are equal to inverse sine of our m times lambda over d. Now, the slit separation d is going to have to be the same here because they all have the same two slits. It's just white light going into the same openings. M for each of the fringes that we focus on will also be the same. But notice the other variable lambda, that's our wavelength, and that will change depending on what wavelength of light we have, right? We just saw an example with red light, where the red light was around 660 nanometers. So that's for red. But we know that visible light goes from about 400 nanometers all the way up to about 700 nanometers. So red is on the 700 nanometer side of the spectrum. But it's possible that we have green would be somewhere in between. I think it's about 550. Since they mentioned green. So since it's a different wavelength, if you have a larger wavelength with this inverse sine, you're going to get a larger angle. If you have a smaller wavelength, you're going to get a slightly smaller angle. It's not a huge difference, but it's something that can be noticed as you go further and further of the center. They're going to spread more and more out. But at the very center, at m equals 0, all of this expression goes to 0. So all of the colors, wavelengths of light that make up the white light will constructively interfere at m equals 0, and we produce the white light. We'll wrap it up there. Next time we'll get to see how we can see some thin film interference effects. But this brings us through Young's double slit experiment.